Welcome back. We're ready for confidence intervals. A confidence interval provides an estimate for a population parameter along with a margin of error that gives a plausible range of values for the population parameter. This confidence interval is, in general, x bar, so our sample mean, plus or minus an m, where m is this margin of error. And to get there, we have some more notation and some other ideas to get to. The notation, just to remind you, mu is an unknown population mean, sigma, an unknown population standard deviation, n, the number of observations in a sample drawn from a population, x bar, sample mean from a population taken from a population, and s, calculated sample standard deviation. We have a new distribution called the t-distribution. The t-distribution is symmetric, it's bell-shaped, centered at 0, very close to the normal distribution, but has an additional parameter called degrees of freedom. Tails are thicker than those of normal distribution, and that adjusts for the variability of using an estimate. When the degrees of freedom are large, t and z are virtually identical. And by the way, degrees of freedom is equal to n minus 1. And we can see how the t approaches the normal here in this graph as the degrees of freedom increase. We see the tails get thinner and the peak get higher. A 95% confidence interval for a population mean mu based on a single sample with mean x bar is x bar plus or minus t star times the standard deviation divided by the square root of n. A 95% confidence interval corresponds to the point in the distribution where there's 2.5% left in both the tails. So in each tail, there's 2.5% of the distribution. The text uses the R software. We are going to use the tables, and I'm going to show you how. The next slide. On pages 466 and 467, there are 2 pages worth of tables. You'll notice that there's not a positive and a negative. It's symmetric, so the one works for the other. And you should notice that the degrees of freedom just continue on the second page. First, we need the degrees of freedom for the critical value we're trying to find. In this case, we had an n equals 10, so 10 minus 1 is equal to 9. Next is to find the confidence level. So we're looking for 95%, which means that on a two-tailed test, there'll be 5% left over. So if you look at that two tails line, you see the 0.050, that's 5%. Then we find the point where both of these meet. So 9 degrees of freedom, 0.050. That means we have a critical value of 2.26. The confidence interval for mean weight from the last video is calculated as x bar plus or minus t star times s, standard deviation, divided by the square root of n. If you don't recall the standard deviation formula, I've got it on the screen right now. You might want to write that down. The square root of n is, of course, the square root of 10. So in this case, we have 63.639 plus or minus 2.62 times 10.031 divided by square root of 10, which works out to 56.46 and 70.82. We could also find a, say, 99% confidence interval or a 90% confidence interval by simply changing which column we look at for the critical value in the table. It's very important to interpret this correctly. The interval will, on average, contain the true population parameter, the true population mean, 95 times out of 100. The key to this is that the population mean does not change. The population mean is fixed. So it's not that the population mean is incorrect or that it's going to change. The population mean is what it is, and our interval is what we're uncertain about. There are, of course, assumptions underlying this test. The first is that the data used was taken from a random sample from the target population. This is why I'm always saying in quick words about how, assuming it's a good sample or something to that effect. And while the population mean from the target population is not known, the target population is well defined. It needs to be normally distributed.